Okay, have you ever been driving through a long mountain tunnel and had that little fleeting thought, what in the world is holding all of this up? Well, today, we're going to pull back the curtain on the incredible, invisible engineering that keeps millions of tons of rock from, well, coming down. We're decoding the unseen strength of tunnels.
I mean, really think about that for a second. When you carve a massive hole through a mountain, you're literally fighting against these immense geological forces that are constantly trying to squeeze that hole shut. So, what's the secret weapon? What do engineers use to win this battle against gravity and pressure?
Well, the answer is actually surprisingly simple, but it is incredibly powerful. It all comes down to this piece of hardware, right here, the humble rock bolt. Yeah, it doesn't look like much, I know, but this thing is pretty much the key to modern tunneling. It is the absolute unsung hero of underground construction.
So, what does it actually do? Well, picture a fractured rock mass like a loose stack of books. A rock bolt is basically a giant pin that you drive through all of those books, clamping them together into one solid block. It literally stitches the rock to itself, creating this incredibly strong reinforced arch that can then support its own weight. Pretty clever, right?
Here's a way to think about it that we can all relate to. You wouldn't hang a priceless, heavy painting on a tiny little screw without being absolutely sure it could hold the weight, would you? Of course not. It's the exact same principle here, just with mind-boggling stakes. The painting is an entire mountain, and the screw is our rock bolt. We have to be 100% certain it's gonna hold. And that brings us to the trial by fire for our rock bolt. It's a critical procedure known as the pull-out test. This is the moment where engineers don't just hope a bolt is strong enough, they prove it. They literally try to rip it right back out of the rock with an immense amount of force. Now, to do this, you bring in some serious equipment. The muscle comes from a powerful hydraulic jack that applies tons and tons of pulling force. A reaction frame braces against the rock face, making sure all that force is pulling only on the bolt. And to track what's happening, a super sensitive displacement gauge measures even the tiniest, most microscopic movement. So, here's how it goes down. The process itself is super methodical. They don't just yank the bolt all at once. Nope, the load is applied in these careful, gradual steps. At each new level of force, they hold it there for a full minute, just watching that gauge to see if the bolt moves at all. They keep repeating this, step by step, ramping up the force until they either hit the target or something gives way. Okay, so running the test is only half the battle, right? You have to know how to read the results. How much movement is too much? How much force is enough to pass? This is where engineers turn to the official rulebook, what they call the acceptance criteria. This table, which is based on the official Indian standard, lays out the hard numbers for what counts as success. It's got these exact targets for how much the bolt can move and its ultimate strength. This isn't guesswork, it's a straight-up pass-fail exam based on decades of engineering science. Let's break down the two most important numbers here. First up, displacement. When the bolt is being pulled with the full force it's designed to handle inside that tunnel, it is not allowed to move more than 5 millimeters. To put that in perspective, that's less than the width of a standard pencil. Any more than that, and it's a fail. It has to be incredibly stable. Second, and this is really the big one, is the safety factor. The bolt has to prove it can withstand at least 1.5 times its design load. That means engineers are building in a massive 50% safety margin. It's kind of like an elevator that's rated for 10 people being tested to hold 15. The system is tested not just for the load it will face, but for a load that's way, way higher, just to be absolutely certain. Now, here's where things get really fascinating. There's this idea of a good failure. See, grout is the cement-like stuff that glues the bolt into the rock. If the test is pushed until something finally breaks, engineers actually want the bond between the grout and the rock to fail. Why? Because it tells them they've found the absolute maximum strength of the surrounding rock itself. And that is incredibly useful data. But if the bolt just slips out, that's a bad failure. That means it wasn't installed right in the first place, and that's a serious problem. So, let's just zoom out for a second. Why go through all this trouble for a few steel bolts? Well, because the integrity of a massive tunnel, or a sprawling new metro station, or a high-speed railway line, it all depends entirely on the proven performance of these small components. This one test is a direct link to the safety of every single person who will ever pass through that structure.
And of course, out in the real world, it gets even more complex. First off, engineers have to think about the local geology. If you're dealing with weaker, more fractured rock, you're going to be doing a lot more testing. They also have to account for different types of bolts, like self-drilling anchors, which are really common these days. And safety isn't just the goal, it's critical during the test. These machines are dealing with enormous stored energy, so they have to be shielded properly. And finally, this whole process is governed by official national standards, ensuring every test on every major project is done exactly right. At the end of the day, it all comes back to this one powerful idea. We can build these magnificent, massive structures that will stand for generations, all because we have a rigorous, scientific way to verify the strength of the very bolts holding it all together. It really makes you wonder, doesn't it? From the bridges you cross to the buildings you work in, our world is held together by countless hidden tests and invisible standards just like this one. So the next time you find yourself deep underground in a tunnel, you'll know